Welcome to this session on trig problems in 3D. Today we're gonna look at some tools and techniques to solve these problems. We're gonna revise the formula for the sin, cos and area rule, and then we will do two examples which use the sin, cos and area rule. Okay, so let's start at the first thing you need to look out for in any diagram. You'll have to look for the 90-degree triangles and then the other triangles which don't have any right angles. For the 90-degree triangles, you'll just use normal sin, cos, and tan, and for the others, you use the sin, cos, and area rules. Sin, cos, and the sin and cos rules will also work for the 90-degree triangles, but it's overcomplicating things. Okay, then in the triangle, there's usually one or two missing link or hidden sides. It all depends what you want to call them. I normally call them the link side. They connect triangles, but are not mentioned in any of the equations. Then another useful tool to think about is the sin of 180 degrees minus theta is the sin of theta. And then finally, double angles. So those are the things that you'll normally use to solve the problems. Now we're going to go to the slightly more general things. Quite often in the answers that you have to prove, there are hints to what to do to get there. We'll highlight them in the examples that we're going to do. And then finally, you have to use what they give you. So normally they don't give any information that's not going to be used. So anything that's there should normally be used. Okay, so now let's look at the formulas for the sin, cos, and area rules. Okay, we're going to start with our triangle ABC, and opposite angle A is side A, opposite angle B side B, and opposite angle C side C. Now, the first formula is for the cos rule, and we apply the cos rule where we have two sides and an included angle. Okay, two sides and an included angle. We will also use this for the area rule a bit later on. And you can obviously write this as c squared equals to a squared plus b squared minus 2ac cos of b, and c squared equals a squared plus b squared minus 2ac cos of c. Okay. But this is the general formula, and all these formulas that I'm going to mention will be on the formula sheet that you get in the exams. Then we will move to the sin rule. There are two sets of equations that look very similar. And the first one we will use if we want to find an angle. The second one we will use if we want to find a side. But you could still find an angle if you use this set of formulas or equations, and you can still find a side if you use those. Okay, and then finally we just have the area rule. So this is the area of triangle ABC is half A times C times sin of B. Okay. So B is the included angle in our diagram above, and A and C are the sides next to the angle. Okay, so those are the formulas. It will be useful if you remember them, but you don't need to remember them because they will be given to you in the exam. Okay, now we can look at our first example. Okay, let's look at the quadrilateral that we're going to work with. Now, it's ABCD, and AB is equal to 17, BC is equal to 17. So the ABC is what we would call an isosceles triangle. Okay. If we find this angle BCA, we will definitely then know angle BAC as well. So when I look at this, I start to look for any clues that might be useful later on. Secondly, they give me on this side a side of 13, an angle of 75 degrees. But that's all. Normally we need two angles in a side or two sides in an angle. So that brings us to this side AC, which will normally be called the link side. You'll see in this example, they actually ask you to calculate it, so they try to make it easy for us. Okay, so let's go to the information as given by the question. So they've got the diagram below. ABCD is a quadrilateral with diagonal AC drawn. AB equal to BC equal to 17, AD is 13, angle D is 75, angle B is 105. So all the information that they give us there is actually put into the picture as well. It doesn't always have to be. Now let's go and start with the area of triangle ABC. Area of triangle ABC. So we'll say area triangle ABC. Okay. Now we have to look for what information we have. So our included angle is B, and we have two sides next to it of C. So it will be a half times 17 squared, because there's two 17s that we multiply, times sin of 105 degrees. Okay, so that's all we have to do. Let's pull the calculator closer. So it will be a half times 17 squared times sin of 105, which is 139.58. 139.58, and the units will be meters squared. Okay. So the next bit is to find the length of AC. Okay, so length of AC. So that's done. The length of AC is this side, and we've got an angle opposite it and two sides adjacent to the included angle, so we can use the cos rule. Okay, so we can say AC squared is 17 squared plus 17 squared minus 2 times 17 squared cos of 105 degrees. Okay, so that 17 squared is just 17 times 17, and we will do this as 17 squared times 2, because we've got two of them, minus 2 times 17 squared times cos of 105. Okay, that gives us 727.58. So AC squared is 727 times 727.58. So AC is just the square root of the answer, which is 26.97 meters. Okay. Now I know we will need to use the side again, so I'm just going to store it into M. Let's say M is for missing side. Okay. And then we don't have to write all the decimals and work with rounding errors. So the next thing to calculate is the size of angle ACD. Okay, so the size of angle ACD. Okay, so how will we do that? So we now know this side is 26.97. So we have a side opposite this angle. We've got that side opposite the side this unknown angle, which means we will use the sin rule. Okay, so the sin rule. So we're looking for an angle, so I'll say sine of ACD over 13 is equal to sine of 75 degrees over 26,97. That's my M. So I can say sine ACD is equal to 13 sine 75 degrees over 26,97. Okay, now because of the fact that angles bigger than 90 degrees for sin is also positive, we need to make sure whether this angle is less than 90 or more than 90. Now it looks like it's less than 90, and to be sure that it's less than 90, the smallest side is across from the smallest angle, and the biggest, longest side is across from the biggest angle. So we can see 26 is bigger than 13, which means this angle will be less than 75. So we don't have to worry about subtracting it from 180. Okay, so let's just work this out. So it will be 13 sin 75 divided by my M, which I stored, which is 0,4655. So that gives angle ACD is shift sin of our answer, which is 27,74 degrees. Okay, so there is our angle, and the last question that remains is just why is ABCD a cyclic quadrilateral? So why is it a quadrilateral? There's a few different ways to prove a cyclic quadrilateral, but we're interested in the opposite angles of this quadrilateral, which add up to 180 degrees. Therefore, it's a cyclic quad. As you can see, it's a bit of geometry used in trigonometry. So don't be thrown by that or think there must be something wrong. You should be able to bring in any part of mathematics into trigonometry or in geometry, and it just makes you think a little bit. Now we can go to our next question, which is going to be slightly harder. So we've got, let's look at the diagram. I will just paraphrase what the question says. We've got a netball pole and two players, A and C, on the field. BA is K, the angle of elevation is from A to P is Y, from C to P is X, and yeah, this angle ABC is 100 degrees. They also gave us that angle is 90 degrees, so when we look at that, we have to think, okay, this is a 90-degree triangle, so we can just use sin, cos, and tan. Now let's look at the question. So the diagram below, vertical netball pole, PB, and its angle of elevation from A is Y degrees, and from C to P is X, and A, B, and C are on the same horizontal plane. So we will call that horizontal plane the playing field of the court, or the court. Okay, now then they say show BC as K tan Y over tan of X. Okay, now let's look at hints they're trying to give us. Tan is opposite over adjacent, so we can already see PB is our link side because it doesn't appear down here. Okay, and we will use tan of this angle here. And then tan of x makes us think, okay, it's opposite over BC. Need the BC. And because it's in the same plane, that angle will also be 90 degrees. Okay. So it looks like we will be able to do this without too much difficulty. And then later on, we'll look at 1.2. Okay. So let's start in this triangle PBA. And we can say tan of y is equal to PB over K. So we can write PB is equal to K times tan of y. Now you need to be very comfortable to change the subject of the equation in these questions because it happens frequently. Now we can look in our triangle PBC, and we can say tan of x is equal to PB over BC. Okay, there we have our BC. So I'm just going to make BC a subject of the equation, so that becomes PB over tan of x. Okay. Now, in the question, there's no PB, so we need to change the PB to something. But as you can see, PB is just K tan y, which is the same as what they want in the answer, which leaves us with K tan y all over tan of x. So that's our first part proven. Okay, so sometimes we need to work out the value of K and the value of BC using this, but in this example they actually give us the value of BC, which is 4,73, and the value of K, which is 3. And so we have two sides that includes an angle, so that's the cos rule, and we can work it out straight away. So we can say AC squared is 4,73 squared plus 3 squared minus 2 times 3 times 4,73 cos of 100 degrees. And we just put that into the calculator. So 4.73 squared plus 3 squared minus 2 times 4.73 times 3 times cos of 100 degrees, which is 36,30, which is slightly more than 36. So we expect AC to be just more than 6. So square root of our answer is just 6,03 meters. Okay, and there we finished the questions. Enjoy. Thank you very much for your attention. Goodbye.